Hey everyone, welcome to our next video. So for this one, we're going to be going over, widen my screen. This one is R3, and this one is called Rational Exponents and Radicals. And so in our last section, we talked about integer exponents, so like whole number, basically exponents, positive, negative, or also zero. Now for this one, we're going to talk about rational exponents. So that's going to be like fractions, like fraction exponents, and seeing what happens there. So I have some definitions and stuff like that to write first. So if n is a positive integer, and a to the power of n is equal to b, then a is called the nth root of b. Basically what we're demonstrating here is this pattern. So let me show you like with some numbers just to kind of help you make sense of it. So if I say that a squared is equal to b, this is the same as me saying a is equal to the square root of b. If I say a cubed is equal to b, this is the same as me saying that a is equal to the cubed root of b. And so then if you have like a weird number or something like that, so like if I said like a to the fifth, we would say that this is the fifth root of b. So that's why we call it like the nth. So it's just because when you get bigger than 3, like for 2 and 3, you say square and cubed and stuff like that. But once you get bigger than that, you're just going to say like fourth, fifth, sixth root, 28th root, whatever the number is. There's another way as well to look at this. So if n is a positive integer, and a is any real number, a to the power of 1 over n denotes the real, just meaning like not imaginary, nth root of a. So an example of this is if I write out to you the square root of a. And so usually we don't see the square root with any numbers. However, what's really happening here is there's an invisible 1 on that a, because anything that doesn't have a power can be written with a power of 1. And then since it's a squared root, there's technically this invisible 2 out here. So I can write this as a fraction exponent and say this is 1 over 2. So roots can be written as fractional, like rational really, exponents. Let me show you if we had like cubed. So if I said the cubed root of a, this is the same thing as me saying a to the 1 over 3. Now, later we'll also talk about what if there's actually like another number involved in this. Maybe I'll write it now. Yeah, let's just do it now. So if I have like 5 root, like the 5th root of b, and let's say to the 8th power, something like this. So if you notice with the squared root and the cubed root, there's like this invisible 1 right there, and that's what's going in the numerator. So for this one, your 8 would be in the numerator, and your 5 would be in the denominator. So the 5th root of b to the 8th power is the same as b to the power of 8 over 5. So we can do this really with any numbers, we're really only working with positive integers like in the actual spots, but then we can write them as a rational exponent. Hopefully that made sense. Here's the important part. The denominator is the root. Numerator is the exponent in the root. Now, technically, it can be inside, outside as well, but we'll talk about that when we get there. So let's go ahead and look at some examples. So for example 1, I'm just going to go ahead and say simplify, and we'll do a few. So A, we're going to do 4 to the 1/2. We're going to simplify that. B, let's do 8 to the 1/3. C, let's do -8 to the 1/3. D, let's do -4 to the 1/2. And I actually have more than this, but I want to show you this first. So 4 to the 1/2, and like I've said in previous videos, but I want to remind you, before I do examples like this, you should really try to pause the video and work through them yourself, just to see if maybe you do actually already understand this concept, and so you can see where you mess up and like make sure you pay attention to that part in the video. So 4 to the power of 1/2 is the same as saying the square root of 4. And this is equal to 2. So that's it, fully simplified. 8 to the power of 1/3 is the same as saying the cubed root of 8. So the cubed root of 8. Let's think for a second. What can I multiply together 3 times the same number to equal 8? Another really common way of doing this is sometimes we can break the numbers down. So 8 is the same as 4 times 2. And then 4 is the same of 2 times 2. You see how we end up, we could break this 8 up into 3 2's. That means that the cubed root of 8 is 2. Now, I don't need you to show that much work. I'm just showing it just in case we need to, break it down that far. Now coming over to -8 to the 1/3, so that's the cubed root of -8. So this one we're looking for something that we'd multiply by itself 3 times to get -8. And in this case, it would just be -2. Now this last one over here, part D, we're going to have to be careful. This is the square root of -4. We'll do this in 1.3. So we're not going to tackle this just yet. You may know what it is. Really, it's just if you take square roots of negative numbers, you end up with an imaginary number or a complex number. And so we start using I. We won't really get into that until 1.3, but I just wanted to introduce it to you for a second, really to draw a difference between an even root and an odd root. So an even root is going to have issues with like I. So like if that was a square root, or if I had done a fourth root or a sixth root or a 20th root, those even numbers are going to potentially create I. Whereas an odd root, like cubed, fifth, anything like that, it's fine to have a negative inside. So that's really why I wanted to bring that up. And I have some more for us, maybe a little bit harder problems. So let's look at part E. This one says -8 to the 2/3. F, I got 27 to the -2/3. I want us to see what happens there if it happens to be a negative in the exponent. And then 100 to the 6/4. Sorry, I was thinking for a second. I realized I was silent. I can't do that as much in an online class. So -8 to the 2/3. So I'm going to write this as a root first. So the bottom number is with the root, so it's a cubed root. And then the numerator goes like as an exponent. So it'd be -8 squared. Now there's really two ways to do this one. You can either deal with the root first or you can deal with the exponent first. So my preference is actually to deal with the roots first, usually. The reason for that is, so I actually almost write it kind of like this, where like I do the exponent on the outside. Sometimes it just really depends on the problem, but these are equivalent ways to write this out. The reason I want to do the root first is because I can do the cubed root of -8 and it's going to make my number smaller, and then I can square it and get bigger. So really this class is made to be done with no calculator. So I want us to practice getting smaller with a number before we get bigger. That way we don't rely on a calculator as much. So cubed root of -8 is -2. And then we square that. So -2 squared is 4. And you could have also done it the other way. So you could have said, okay, cubed root -8 squared would be 64. But then you got to think of the cubed root of 64, which is also 4. But I think it's better to make your numbers smaller, and then you can make them bigger, you know. All right, next up, we got 27 to the -2/3. All right, we got to be careful here. That negative in the exponent means that we're going to flip into the denominator, is what's really happening. So let me write this a different way for you. And I could have written it like this for part E too, I just didn't. What this is really saying is I have 27 to the -1/3 squared. Now I don't know if that intimidates you, like seeing it separate like that. But you can always break these up. So you could do 27 to to the -1 to the 1/3 squared. Like we can break it up really far and kind of piece it together, you know? That might look a little confusing to you, so I don't always do that, but really what I would do for this one is I would say, okay, the negative is going to bring me into the denominator. So that's going to make me have 27 to the 2/3 in the denominator. I can't leave the numerator empty. I need a placeholder. 1 is going to be our placeholder. And then I can write it out as cubed root 27 squared. Now the process of breaking it up, that's what kind of makes it like obvious to you that we're using the theorem up here, like the 1/n thing, because it's really just 1/3, but I don't know. I think that looks more confusing. So with this cubed root of 27 squared, I'm going to do the cubed root of 27 first, and then I'll square it. So cubed root of 27 would be 3, and then I'll square it, so I get 1/9 as my answer here. And I think that's a lot better than having to do 27 squared, and then you try to figure out the cube. That might be hard. Not if you have a calculator, but really this class is meant to be done without one, so. And then for our last little part on this example, see how it's 6/4? Don't be intimidated by bigger numbers like that. That fraction can actually reduce. So think for a second, what does 6/4 reduce into? Be 3/2. And then we can write this with a radical, so it'd be the square root of 100 cubed. But again, I can do the root first to make it smaller. So square root of 100 is 10, and then cubed would be 1,000. Let me also tell you this here. It's very possible that I'm going to show you more in this section than the homework actually asks you. Um, when I'm thinking about prerequisite material, I'm really trying to think about anything that you could see, not even just in this class. You know, I'm also thinking about, you know, what classes you might take later. And I have lots of different students who take 101, so I try to keep that in mind. Um, so sometimes, you know, I might do examples and you're like, man, the homework didn't even get to that. And that's fine. It still means it could be on the test. Just because it's not on the homework, it could still be on the test. It's just maybe I went a little further than what I asked you on homework. Okay, I'm going to give you another property here. It's really just one, so property. So if we're looking at something where maybe we have the outside of the radical and then the power, what if they're the same number? And also this one is highlighting if we stick with A. So I'm going to show you some examples, you know, that use this, but if the n is even, then this would equal the absolute value of A. If n is odd, this will just equal A. So you won't need the absolute value. I want to tell you a little bit of why you may use this. Specifically, if you are an engineering and science student, if you are going to take Math 241, this actually comes up, this idea of a root having to be written simplified with an absolute value on it. And so that's something that you'll deal with later, but uh, it's really just an algebra topic. And so I'm going to show you why and stuff as we do our example. So let's go ahead and get into our example. That way we can see what's going on here. Why do we care? Not simply, simplify. There we go. And so let's say for this one, part A, I say 64a to the 6th, and then I want to take the 1/6th root. Like the 1/6 is the exponent, so it's going to be the 6th root. So remember that this goes through, like if you have stuff multiplied in a parentheses, the exponent goes to all of it. So this is 64 to the 1/6, and this is also a to the 6th to the 1/6, or just 6/6. 64 to the 1/6, so I'm taking the 6th root of 64. And then a, that'll be to the power of 1. So again, just in case that was a problem, I multiplied these together. So I multiplied those exponents. 6 times 1/6 is 6/6. That's how I turned it into 6/6, and then it turned into 1. Now the 6th root of 64 is 2, and then a to the power of 1 would just be a. Here's the problem here. If I say that I can do this for any a value, like it doesn't matter, I'm actually going to have issues. Let me try some stuff. If a equals -1, let's go ahead and see if this is true. So if I do 64 -1 to the 6th to the power of 1/6, does this equal 2 times -1? So I'm trying to see, is the original, if I plug in -1, does it equal the ending when I plug in -1? So I'm going to simplify here. So 64 -1 to the power of 6 would just be 1. 2 times -1 would be -2. So here I get 64 to the 1/6 equals -2. So this gives me 2 equals -2. But that's not right. Now if I plug in a is equal to +1, then it'll work. So I'll get 64 1 to the 6th to the power of 1/6 equals to 2 times 1. This is going to give me 64 times 1 to the power of 1/6. 64 to the power of 1/6 equals just 2, and it's equal to 2 on the other side. This checks out. So here's the idea. If your root and your like exponent on there, if they are the same number, if the n is even, you have to use an absolute value of a. Because if we had added in an absolute value right here, it would have made that -1 positive, and then it would have held true. So I know that might seem a little confusing. It's just because when we are left with a variable, we want to make it clear that you're actually not allowed, like you actually do have to be careful if you want to plug in whatever you want. Like if you want to plug in whatever A you want, we need to be able to fix it in some way to actually make it true. Because just now I was like, well, if I plug in a -1, it doesn't work. So that's the idea. So let me go ahead and box this in. The final answer here is 2 absolute value of A. Let's do another one to see what happens. This one says x to the 9th to the power of 1/3. So this one, they're actually not the same, but we still need to check this kind of stuff. And it's really just when you are left with a variable inside. If you're left with a number, you're just simplifying and that's it. This is really just if you have a variable. This idea is actually going to come up later as well, because sometimes we'll like plug in certain, like we'll like solve for something when we do equations, and we're going to get things that don't actually work if you plug it back in. And it actually comes back to this idea. So if I simplify this, so I have, oh, I like to use my other colors. So I would have x to the 9/3. So that simplifies to just x cubed. And so I'm wondering, do I need to put like absolute value bars on here? Do I need to be picky about the x's in this? And so I'm going to check. So if I let x be -1, or if I let x be +1, do I get the original equals the answer? So let's see. -1 to the 9th to the 1/3. Does that equal -1 cubed? So if I simplify this, -1 to the 9th is just -1. -1 to the power of 1/3 is the cubed root of -1. That's still -1. -1 cubed is -1. So this checks out. If I plug in +1, I get 1 power of 1/3 equals 1. Yep, this one is also working. So this one, I don't need it. So no absolute value bars needed. This one's fine as it is. I can just box in x cubed. We'll do one more like this. This one is y to the 12th to the 1/4. So I simplify, I get y to the 12/4. That would just be y cubed, but I got to check, do I need absolute value bars here? So let's see. I'll plug in -1 and I'll plug in +1. I'm just picking -1 and 1 because they're easy to plug in. And it's going to make sure it shows us like, do both of these work? So if I plug in -1, let's see, I get -1 to the 12th and then to the 1/4 power. And then if I plug it in at the end here, so into y cubed, I get -1 cubed. So -1 cubed is going to give me -1. On the other side, -1/12, I get 1. And then to the power of 1/4. Ooh, so that's giving me 1 equals -1. No good. That means I need absolute value bars. So I'm going to go ahead and put absolute value bars around my variable. And so what that does is it makes it to where now this -1 is going to have, well, let me put them on the outside. This -1 cubed is going to have absolute value bars. So now it'll be 1 equals 1, and it'll be good. Won't have any issues. So again, you only have to worry about the absolute value bars. Um, Really, it's when you're dealing with even roots is when it's going to happen. And then also when we have like a variable. It's not when you have numbers and stuff, you don't have to worry about it as much. So we'll keep going. I usually am going to say something to key you in to the fact that we might need absolute value bars or something. Um, Honestly, I don't usually put that kind of thing on the test. I like to be pretty transparent. I'm probably not going to ask you about that on the test, like the absolute value bar thing. I usually like to just say all variables represent positive numbers, so we don't have to worry about what happens if we plug in a negative. So, just a little thing for you to know. But we are going to do some more simplifying problems just to do some more. Let's see. Do I want to do those first or do I want to use those? We're about to use some more exponent rules. I'm debating whether I want to introduce you to some other rules first. I will keep it separate. Sorry. Example 3. Let's go ahead and simplify these. We're just going to practice using some exponent rules when we have rational exponents. So x to the 2/3 times x to the 4/3. Part B, we'll do x to the 4th, y to the 1/2 to the power of 1/4. And then part C, we'll go ahead and do a to the 3/2, b to the 2/3, all over a squared. And then this is all cubed. So just going back to doing some exponent rules and stuff, but now we have rational exponents. So for part A, and again, you should pause and try to do them yourself. For part A, we're multiplying two things with the same base. So that means we can add those exponents together. And when you add fractions, you add the tops and then the denominator stays the same. You have to have the common denominator to be able to add and subtract fractions. So this would be 6/3. So that's going to simplify to just x squared. Part B, this would be x to the 4th to the 1/4 power, and then y to the 1/2 to the 1/4 power. So since we're only split up by multiplication, I'm just putting everything with that exponent. So x to the 4th to the 1/4, that's going to be 4/4. Y to the 1/2 times 1/4, so that's going to be 1/8. X to the 4/4 is just x to the 1, so I'm just going to write that as x, y to the 1/8, and box that in. Now technically, we might want some absolute values here. I'm not worried about it right now. I'm going to tell you on the test that all variables represent positive real numbers, and so you don't have to worry about it just for our stuff. We're just going to work on simplifying. Now for this last one, part C, I'm going to go ahead and distribute that 3 to everything. So this is a to the 3 over 2 cubed, b to the 2 over 3 cubed, and a squared cubed. Simplifying this, I get a to the, when you multiply these things together, be careful here, this is really a 3 over 1. So when I multiply across, it's going to be 9 over 2. B to the power of 2 over 3 times 3 is just going to be 2. If you're having trouble with the fractions and doing arithmetic with fractions, that's something that is a really prerequisite topic that you might want to look up. And then at the bottom, I get a to the 6th. Now I can simplify this further because I have 2 of the same base. So I'm going to do, we can decide if we want to do 6 minus 9 over 2, or if we want to do 9 over 2 minus 6. I know that 6 is bigger, so I'm going to do that one first. 6 minus 9 over 2. B squared is going to be left up here. Now I'm going to do this off to the side here. So 6 minus 9 over 2. 6 can be written with a denominator of 2 if we multiply it by 2 over 2, because remember it's really over 1. So this is 12 over 2 minus 9 over 2, which results in 3 over 2. So this at the end is going to be b squared over a to the 3 over 2. So again, if you're just struggling with that, like putting fractions and stuff together, you may want to look up some videos on fractions. I can help you as well. Just reach out to me. These are really just more examples, the ones I'm looking at right now on my paper. And so we're going to do them. But now they just have more like items in, like inside the parentheses of like a radical or something like that. So we'll go ahead and do some of these together. So using quotient and product rule, let me show you another rule that we have. And this is assuming the same information about a, b, and n that we had earlier. If you have the nth root of a times b, this is the same as the nth root of a times the nth root of b. So you can split them up. Same thing with division. If you have the nth root of a over b, this is the nth root of a over the nth root of b. So let's do some examples and we'll see how we can use this. part A, let's do 4th root 16 over 81. B, let's do 2 to the 2/3. C, let's do 3x to the 3/4. And then I'm kind of running out of space over there, so I won't write D out yet. So for some of these, we're going to use these rules. For some of them, we're not. I just, like, there's some that are kind of, like part B, we're not going to, but I just like it, so we're going to do it. So for part A, again, you should pause, try to do it. For part A, we're saying that this is the same as 4th root of 16 over the 4th root of 81. So we can treat them separate when we're simplifying. So 4th root of 16 is going to be 2. The 4th root of 81 is 3. So that's it. Part B I like. So this is the cubed root of 2 squared. Now, earlier, I usually do the root first. In this case, I can't do the cubed root of 2. So I'm just going to have to do the power first. So I get cubed root of 4. I can't reduce that at all, so I'm just going to leave it as is. And so that's something, really why I wanted to do it is to show you that sometimes your answers are just going to be left kind of ugly. And that's fine. Don't worry. Next, we got 3x to the 3 over 4. So that's going to be 3 to the 3 over 4, and then also x to the 3 over 4. You can write it like that, or you can write it all together. So we can write it as the 4th root of 3x cubed. Now, I can't take the 4th root of 3. I can't take the 4th root of x. Like, there's nothing I can do there. So I'm going to go ahead and do the cubed first. So that's going to be 3 cubed is 27, x cubed. And this actually cannot simplify at all, so we're just going to have to leave it ugly. That's okay. I'll talk to you about when you can simplify those, though. And another one, let's do D. This one is 2 times x squared plus 3 to the power of negative 1 over 2. E is where we're going to start actually being able to reduce these even further. So let me write this one a little closer here. This is cubed root 125 a to the 6th. And then I have one more in this little like subsection that we got going on. Negative 32 y to the 5th over x to the 20th. Try these out. I'm going to go ahead and get started. So this 2 outside of here is not being affected by this up here at all. So that means it's just going to kind of hang out with us the whole time. So this is 2 over x squared plus 3 to the 1/2, right? Because the negative just puts it into the denominator. And then we can write it as the square root. And there we go. That's it. This cannot simplify any further. I sometimes have students try to cancel these out, like the square root and the squared right here, like they try to cancel that. Not able to do it. The reason is because of that plus on that 3. So you actually cannot do anything with this. You have to just leave it as is. For our next one, I'm going to split it up. So I have cubed root 125 times the cubed root of a to the 6th. Now, cubed root of 125. Can we think of what that is? So that's going to be 5. And then over here, the cubed root of a to the 6th. Sometimes it may be beneficial to actually write it as a fraction exponent, not as a root. So in this case, as a exponent, it would be 6/3, which actually reduces really nicely and just leaves us with a squared. So like sometimes it might be nice to write it as the root. Sometimes it might be nice to write it as the fraction. It just depends. And for our last one on this little subsection, I'm going to split it up. So 5th root -32 times the 5th root of y to the 5th divided by the 5th root of x to the 20th. So for like the number, I think it's nice to see it with the root. That's going to be -2. But with everything else, I actually think it would be nice to see it as like the fraction exponent. So I wrote it as the fractional exponents, and now I'm going to simplify them. So I have -2. That would just be y to the power of 1. This would be x to the 4th. And that's it. All right. Next up in our notes, I want us to talk about simplifying radicals when they're not perfect. That's the best way I can say it. When they're not perfect. What I mean by this is, earlier we did cubed root of 125, and it's perfectly 5. We did 5th root of -32, and it's perfectly -2. What about if it's ugly numbers, or like they just don't reduce very nicely? So I am just going to kind of jump into some examples with these, but we'll start off kind of slow. So I'll still say simplify. So the first one is square root of 20. B will do 24 x to the 8th, y to the 9th. And then part C, we're going to do 9/√3. We're going to talk about how to simplify something like that. All right, square root of 20. Can we break that number up at all to where we could get a perfect square out of it? So ideally, we would say, okay, 20 is equal to 4 and 5. So this means that square root of 20 is equal to the square root of 4 times the square root of 5. And then you could break this up, right? Because the square roots, if it's multiplication, you can break them up. So this is square root of 4 times square root of 5. Well, square root of 4 is 2. And then I just have the square root of 5. Another way to do this problem, let's say that I didn't think of 4 and 5. You know, maybe it's an uglier number or something like that. Let's say I did 10 and 2. Well, then I can break up 10 into 5 and 2. So another way to do this problem is to break up 20 into 5 times 2 times 2. Since it's a squared root, when you get a pair of 2, they can come out to the front. So this would be 2 root 5. Now you got to be careful there because if it was a cubed root, you would need like a triple. So we would need like 3 2's to bring it out to the front. If it was like an eighth root, we would need 8 of the same number to be able to bring it out of the root. Okay, let's do part B. So now we have multiple stuff in here. So if you want, we could break it up and treat it all separate, or we can kind of work with it all together. It's a little bit up to you and what your preference is in showing work. I'm going to break them up so that I can show you like one by one how we're going to do each one. So this is square root of 24 times square root of x to the 8th times the square root of y to the 9th. All right, 24, I'm going to do that one first. So 24 can break up into 4 times 6. So this can break up into 2 root 6. And that's as far as it can go because 6 does not have another perfect square inside. Let's work on the x to the 8th. Now we can write that as a fraction exponent. So this is x to the 8 over 2. So that's going to be x to the 4th. Now y to the 9th is actually a little bit harder to work with. The reason is because 9 does not divide by 2. So like me writing this as y to the 9 over 2, that doesn't help me at all. So we actually have to be a little strategic here. What we're going to do is if you have like a squared root, I want to come down let me word this differently. I'm going to break up y to the 9th so that I can have an even exponent so that I can divide it by 2. Let me show you what I'm trying to say. Y to the 9th can break up into y to the 8th times y. Pause and take that in for a second. Is that okay with you? Then we can break this up further and we can say, okay, now we're dealing with square root of y to the 8th times square root of y. Square root of y to the 8th is y to the 8 over 2. So that's going to become y to the 4th. Now this square root of y is still trapped in the square root. It can't do anything. So let me write for you what we have all together, because I did it in pieces, right? Outside of the square root, we have a 2, we have an x to the 4th, we have a y to the 4th. Left inside the square root, we have a 6, and we have a y. This is fully simplified. Now take this in, you know, if you ever have the power like bigger than the root, you're going to have to simplify that in some way. Now, if this was like me doing this problem, I probably wouldn't show that much work. Here's probably what I would show if I was doing this myself. I would have said, okay, 24 is 4 times 6. X to the 8th won't be a problem. Y to the 9th is y to the 8th times y. For the 4, square root of 4 is 2. Square root of x to the 8th is x to the 4th. Y to the 8th is y to the 4th. And I'm leaving the 6 and the y behind. So I would probably show a lot less work than this. In general, if you show less work, you could miss out on some partial credit, so just be careful about it. Just be careful if you skip steps. The more work you show, the more I can kind of dig into the work and like see what maybe happened if something is wrong. If the question's right, then you don't have to show as much. Now this last one is just kind of another way of reducing like roots. Whenever you have a root in the denominator, the issue is that you don't want radicals in the denominator in general. So a lot of times what we'll do is we'll multiply by the root at the top and bottom in order to simplify. So here we would get 9 root 3 divided by root 3 times root 3 is just 3. So this reduces into 3 root 3. That's something really common that you'll see if you take trig, actually, is like rationalizing denominators. That's what that's called. It's something quick I just kind of threw in here. I'm not sure it comes up on your homework very much. Let's do some operations with radicals. So, operations with radicals. So we've decided that when it comes to multiplication and division and stuff, we really don't have many rules. What if we have addition or subtraction? So if you want to add radicals together or subtract them, they have to be like terms. So for instance, square root of x plus square root of x can add together. There's invisible ones out here, so this would be 2 square root of x's, right? You can add stuff together if they're the same inside the root. So let me write that down. To add or subtract inside root must be the same. Also, the root has to be the same. So like you can't add like a square root and a cubed root together. So let me put that too. Also, root must be the same. There is a way to do it if the roots are different, and we will do one like that. It's just you got to like work around it a little bit. And I'll show you. So we'll do another example here. I think this is number 6. So simplify. There's just so many different like small types in here. So that's why there's so many different examples. First one, let's do root 20 plus root 5. B, I've got cubed root 24x minus the cubed root of 81x. C, we'll do 4th root 4y cubed times 4 12y squared. Here we go. I know I said that weird. Sorry. I didn't like read it very mathy, like in a good mathematical language. Should have gotten some water before I started this video. It's okay. We're almost done. Okay, so you need the inside of the roots to be the same. Now we can simplify to get this done. So root 20. Let's see, how does that break up? So root 20 I'm trying to see how I want to write this just to look nice. So root 20 is the same as 4 times 5. So this is going to be 2 root 5. So for my problem here, I would have 2 root 5 because that's what root 20 is, plus root 5. Okay, well now I can add them together. Remember there's an invisible 1 out here. So this is going to be 3 root 5. There you go. You can put them together. For the next one, I have cubed root of 24x. So I'm going to break this up a bit. So let's see, 24. I'm looking for perfect cubes now. I'm not looking for perfect squares. So 24 perfect cube would be 8 and 3. So I have 8, 3, and x. Cube on this 81 would be 27, 3, and x. So 27 times 3 is 81. The reason I want 27 is because it's a perfect cube. And that's still in the root. So the cubed root of 8 is 2. And then this 3x is left over. Cubed root of 27 is 3. And then this cubed root of 3x is left over. So now since these are the same, I can put it all together. So this is going to be negative 1 cubed root of 3x. I can make that look a little nicer. I don't really need that negative, like that 1 on the outside. I'll just say negative cubed root 3x. Now, if the numbers are hard to reduce for you, so like let's say with 81, let's say that was really difficult to get to 27 and 3. 81 is 9 and 9. 9 is 3 and 3. 9 is 3 and 3. So I can also write this as, instead of square root of 81, sorry, cubed root of 81, I can say cubed root of 3 times 3 times 3 times 3. Since you have a group of 3, you could take it out. So you're left with 3 root 3. So if that gets difficult for you, you can always do it. Like to find a perfect square, perfect cube, you can always do what this is. It's called a tree diagram or prime factorization. That's another way that uh, it's talked about. Let me know if y'all have any issues about any of this, okay? Let's do the next one together. So let's see. I'm just going to go ahead and multiply. So I have 4th root, and I'm going to just put it all together. So 4 times 12, that's going to leave me with 48. Y cubed times y squared is going to leave me as y to the 5th. Now I got to reduce this. Does 48 have a perfect 4th in there? You know, honestly, I don't know offhand. So let me go ahead and do the breaking up method to try to see. So let's do it. 48. Let's see. Well, 4 and 12 were good. Let's go ahead and do that. Leave it as 4 and 12. Sometimes maybe it wasn't that helpful to write them together. You know, maybe it was better to leave them apart. Y to the 5th, I need it to be divisible by 4. So I'm going to make this into y to the 4th times y. That way I'll be able to do 4 over 4 and actually reduce that. That's the goal. All right, let's see. 4 can be written as 2 times 2. 12 can be written as 4 times 3. Okay, I'm getting somewhere because then I can break that 4 up again. So I have 2 times 2, and I'm breaking up this 4 again. So I'm going to do 2 times 2, and then I have 3, y to the 4th times y. So hopefully y'all can kind of see what I tried to do there. I couldn't think of like a perfect 4th, right? So I was like, well, let me just break it up. And now I have this one here, so I can take that out to the front. So that's going to be a 2 out here. This here can come out, y to the 4th divided by 4, right? It'd be y to the 4 over 4. So that's going to leave me with just a y. And then left inside is that 3 and that extra y. So sometimes maybe the work doesn't look as nicely clean and polished, but that's okay. Now I would like to do some where maybe the root is not the same. So let's do some like that. This will be our last example. So we're going to simplify if the roots are not the same. So let's see what we got here. Part A, I'm going to do cubed root of 2 times square root of 3. B, I'm going to do cubed root of y times the 4th root of 2y. And part C, have the square root, the cubed root squared. So I'm going to go ahead and reduce these. You could try them on your own. Maybe if I try part A, like if I do that one, maybe you'll be able to do B and C on your own. You know, you could always try it. So let me do part A with you guys. Hopefully I'm doing it with you. Hopefully you're doing it with me, I guess. You're working on it at the same time. So for this, we're actually going to write it as the fraction exponent first. So cubed root of 2 is 2 to the 1/3. And then square root of 3 is 3 to the 1/2. And so we really need these to be the same. Well, we can always get denominators to be the same. You could just multiply them by stuff. So let me write it a little differently here. I'm going to write it up and down so that it's not confusing for you. I can multiply 1/3 by 2/2. I can multiply 1/2 by 3/3. What this does is it gets me common denominators. So we have 2 to the 2/6 times 3 to the 3/6. Now that these have the same denominator, they can be written under the same root. So this is the 6th root of 2 squared times 3 cubed. 2 squared is 4. 3 cubed is 27. 4 times 27 is 108. And so we were actually able to multiply these even though their roots were not the same. I think these are cool. I think these are fun. It's like puzzly, you know? That's really what math is. It's just a big old puzzle. So maybe go ahead and try part B on your own. Pause the video, but I'll go ahead and do it, of course. I know I've been switching between like blue and pink as my main color. I do that. Cubed root of y. I forget what color I'm using sometimes. This would be y to the 1/3 times, be careful here, this is 2y to the 1/4. Trying to write it up and down for you. Let me write it bigger, actually. I feel like that is like way too small. Let me write it bigger. Y to the 1/3 times 2y to the 1/4. There we go. Maybe that looks better. So I need these to have the same denominator. So 3 and 4, I can get them both to be 12. This is 4 times 4. This is 3 times 3. I get y to the 4/12 times 2y to the 3/12. Well, now they can be written in the same root. So I have the 12th root, y to the 4th. Be careful here. This is 2y cubed. I keep forgetting my equal signs. So y to the 4th. 2 cubed is 8. And then y cubed. So then we're going to be able to put the y's together as well. So there's going to be 12th root 8y to the 7th. Now be careful here. If that 7 was bigger than 12, you would have to reduce this further. You'd have to. And then for our last one, let's go ahead and do this one together. So I'm going to write it all as roots. So this is 2. That cubed root can be written as 1 over 3. And then that square root on the outside can be written as 1 over 2. Well, we just need to multiply the exponents. So this is 2 to the 1 over 6. And writing it like this or writing it as 6th root of 2 are both simplified answers. It just depends on how your answer is asked for, but they're equally simplified. So that one I feel like looks hard, but it actually isn't that bad. It just looks ugly. Now before you go, I do want to show you just one more. I actually put this one on a test once and no one got it right, so I had to throw it out. I didn't have to throw it out, but I chose to throw it out. So if you want to go ahead and try that one, I'll tell you what the answer is. Your answer should be y 12th root 16y. That's the answer. But maybe practice that one on your own and just see if you can do it. All right, so that's it for us. I know this one is a little bit of a random section. Like there's just so many things to do with radicals. It's just like radicals like thrown up on you is what I feel like for this one. Um, if you are having any questions, please feel free to reach out to me. We can always make a Zoom meeting. You can come in if you're on campus, that's fine. I will tell you that right now in my office, it is 76 degrees. So I can't say that coming in here is awesome. But yeah, I hope you'll have a wonderful day and I will see you in our next video. Bye bye.